Santosh Reddy, நீங்க எங்க இடத்துல
will come, I'll go out and then.
அந்த பொசிஷன்
I welcome everyone for the session 2, day 7, tutorial 6 session. Here this session we are going to talk about the, I can say, hot thermal plasma as well as the cold thermal plasma. So it's something like a case study, how this is going to be demonstrated by using the, I can say, the system available in our laboratory. So the system, hot thermal plasma, the system is available in our thermal laboratory. It has several components. So it has several components. Starts from the plasma generator, plasma reaction chamber, plasma generator, then the synthetic gas cooling unit, wet scrubber, misty eliminator, air compressor, nitrogen cylinder, scrubbing solvent tank, three-phase power supply for creating the high intensity spark, temperature indicator, gas outlet from the reactor, feed door, plasma torch, ash removal door, and thermocouple to measure the temperature at various points. So this the schematic diagram of the experimental facility for treating the different biomedical waste is presented here. So the system is operated in 3 different modes. We can operate in a combustion mode, we can operate in gasification mode, and we can operate in pyrolysis mode. So what is the fundamental difference among this? We are going to provide, we are not going to restrict the air quantity. General oxidation process, we are providing the oxygen, which is slightly more than the complete burning of the raw material what we have used. So we can have the flexibility. It is a universal reactor actually, which can able to run it in both combustion mode, gasification mode, and pyrolysis mode. So here, based on the combustion mode, is generally we call this the incineration system. In the incineration system, we are simply burning out the raw material, converting into I can say heat. The heat may be recovered, but the pollutants what is coming out from the reactor is having a lot of, I can say, issue in terms of to the local environment. So incinerator, I can say we can convert the, I can say, harmful raw material into, I can say, some kind of heat generation, which can able to recover it by in the form of, I can say, converting into steam or converting into hot water, which can be used for the different medical, I can say, hospitals. Whereas suppose if you want to, I can say, control the toxic emission comes out after the burning, we cannot go for, I can say, combustion mode. We can go for either gasification mode or, I can say, pyrolysis mode. The gasification mode, the given raw material is operated with the 20 to 30% of the stoichiometric air fuel ratio. We can control the equivalence ratio of the I can say, we can control the equivalent ratio. We can operate between 0.3 to 0.4. So we call it as the gasification mode, I can say. In the gasification mode, the products of the gasification will in the form of solid, liquid, and gaseous things will comes out. In general, it is only two products. One is called solid and another one is called gas. The condensable gas, we can say it is a liquid. The non-condensable gas, we can say is a synthetic gas, along with carbon dioxide and other trace of gases will be comes out in the products of the gasifier system, which can be used in either in the thermal producing the heat, or we can use it in the engine for producing the power. And as you all know that if you go for gasification mode, this amount of the heat comes out from the non-condensable as well as the condensable gas, which can be recovered. And also for non-condensable gas, we can use it in every hospital. Suppose we are want to install this in any hospital, we can use it as a fuel for producing the heat for different applications. Another mode we can able to say that we are not going to supply the air. We are not going to supply that. The total system is operated in inert atmosphere. In that case, we are not to eliminate the oxygen presence in the reactor. We are sending the nitrogen from the cylinder. So nitrogen will be thrown into the reactor and it purge out all the air particles available in the reactor. So the given raw material, maybe you can add any kind of any type of raw material. Purposefully, this reactor was designed for treating the medical waste. So the raw material, I can say, is fed into that, and nitrogen will be acting as a shielding gas to avoid the I can say oxygen entering into the system. It's an endothermic process, whereas gasification combustion is the exothermic process. The endothermic process, you need to provide the heat. The heat can be provided by the form of, I can say, from the external source, from the form of electrical input. So we are going to create, I can say, the plasma by using a plasma generator. So similar to the cold plasma, here also we are maintaining the gap. What is the advantage we are proposing in this system is we are completely eliminate the noble material platinum. So we converted the platinum material into low cost copper material, and the copper is used as a electrode for creating the spark. The gap can be adjusted in such a way that we are producing, I can say, high current, low voltage. The hot thermal plasma system. And also it is a equilibrium. We are maintaining the equilibrium. That means the electron temperature we are maintaining equivalent to the ionized gas temperature. Here, the principle of working is we are creating the spark. So the spark is the total system is covered with nitrogen. So nitrogen, the spark will be penetrated into the nitrogen. Nitrogen is converted to ionized gas. The ionized gas is used for heating the raw material. So only very near to the core we have high temperature. Then outside of the core we have I can say the normal the combustion temperature. From that we can able to convert all the material present. Medical waste contains different materials in the form of the plastics or the paper and cardboard and wooden material and iron material, right? Then different blood, bones, everything is there. What the advantage in going for this kind of the plasma reactor is there is no need of segregation for any medical waste generated from the hospital. So the major cost involved in I can say the treatment of the medical waste is one of the major parameter is that the segregation of the waste. So here we are proposing that we are not going to segregate any waste. Whatever is coming out from the hospital, we are simply, I can say, put it in the reactor. Everything will be because of the high temperature, everything will be converted into gas. But some material which can able to withstand high temperature can be melted. It will be cut. We will get in the form of the product, which will be the form of solid, which also has the revenue in terms of selling to the market. But I hand over to the Uday Kumar. Uday Kumar, you can give the demo of that.
We have a plasma reactor. usually call this as a universal plasma reactor. Universal plasma in the sense here, as Star said, here we can do all thermochemical process in a single reactor by simply switching the medium. By simply switching the medium, we can alter the process. All thermochemical process together can done by this reactor. This is 1 kg reactor. This is 10 kg reactor. So both are available. So here the thermochemical reactor. Thermochemical reactor majorly contains 4 components. First thing is first important component is plasma generator. Here we are giving electrical power. That electric power converted into DC. That DC low voltage. Here we are giving 3-phase supply, so 440 AC to 120 DC. That 120 DC is supplied to the electrode through electrode. So one is high voltage electrode, another one is ground electrode, as like cold plasma, what we discussed in previous tutorial. But here the voltage difference is, voltage is high voltage is 120 only. But in cold plasma cases, we go with the kilovolt range. So here we are giving 120 volt in one end of electrode, another electrode connected with the ground. So between the electrode, by minimizing the gap or by adjusting the gap, we can initiate the R. So after R initiation, after R initiation, it will give huge amount of heat as well as excited elements that may contain electrons or ions. So that will promote the reaction that will completely demolish or completely decompose the waste, whatever that. Medical waste may contain pathogens or medical waste may contain different foreign materials. We could not tell medical waste may contain diesel. It may contain blood, it may contain pathogens, it may contain body fluids, it may contain metal shards, it may contain glass. So whatever exists, it will decompose and it will convert that into gaseous and very minimal solid residue. So that solid residue is very minimal. For our case, it may go beyond 99%. If you put 100 gram solid waste, it will convert it into 1 gram of solid residue. So that much complete degradation happens. If you go with pyrolysis or gasification, means the solid residue may be 5 to 10%. But for this case, it will be very minimum. For incineration also, we will get around 6 to 7%. Some unburned may be there, but here it won't exist. So here, if you look at the reactor, this is high voltage probe, this is ground probe. So between high voltage and ground probe, we are maintaining the voltage and the current. Here we can, in that case, in cold plasma case, we can adjust the voltage. But for here, we can adjust the current. Here we can give around the current from 20 amps to 70 amps. This range may vary 20 to 120, 20 to 180. Depends on our scalability or depends on our requirement. We may give different capacity plasma generator. So now we saw the simple demo how to generate hot plasma by this setup. You can turn on the. Okay, before moving to that, here you can see 3 chambers. The first one is cyclone separator. That cyclone separator helps to train the density difference particles that may strain the heavy particle here. Then second one is wet scrubber. In wet scrubber, we are scrubbing like HCl or some other pollutant may. That means you can use any of wet scrubber, or else water may use. So water may drain the nano-sized suits. So here heavy particles collected. Here thin gas is completely cleaned, and then this is mist eliminator. Why we are using mist eliminator means after scrubbing, this is direct scrubbing. So water is directly meeting syngas. So if direct meeting water, syngas may capture moisture or syngas may carry some quantity of water. So that water will affect the calorific value of syngas. So we could not utilize for further application. So that we are using mist eliminator. Mist eliminator, it has a powerful structure. It's like jet safe. So it will condense the water which is present in the syngas. So it will drain down, and then we can get a clean syngas. That may be a combustible fluid. If I operate this as a if I operate universal reactor in combustion mode, I mean gasification mode. If it is combustion mode means you can give sufficient oxygen in the sense sufficient air it can supply. Then clean flue gas will come out. That clean flue gas contains only CO2. Other than CO2, everything is eliminated. So actually, in global warming potential case, CO2 is equivalent to CO2 is equivalent to 1 kg CO2 equivalent. But in case of CO means 5, and then CH4 means 25, NO means 240. So similar way, that multiples will come. So based on that only we are deciding global warming potential. It does not have a unit. We are using CO2 equivalent as a unit for global warming potential. So only CO2 emitted means that is not highly affect the global warming. As Sir said initially, if I use biomass as a resource for hydrogen generation, then I can call that as a green. So similar way, because biomass is taken from tree, it means tree should not be cutted completely. You have to take the residue from tree. The mode of professor said is the residue coming from tree that can be decomposed by through method. Then it will emit CO2. That CO2 may be taken by tree and it will be converted into. It's like a complete structure. I mean, it looks like a complete cycle. So these are all the major components. So now we can have a small trial. Be safe. This is also high voltage, high current, danger than cold plasma. Now it is minimum current. Like here, if you look at the electrode, I will show the video also. I also have already run video that I will show. Like here, you can see the high voltage electrode and the ground electrode. Both are connected. This thing is designed based on guidance and then support. So we have developed this setup for particularly discarding medical waste. So here, this is high voltage electrode. This is ground electrode. The high is connected here. Along with this, here you can see the tube. So from here to inside, I'm for circulating the compressed air. Maybe compressed air, maybe nitrogen, maybe oxygen also we can supply. The oxygen supply means then oxycombustion will happen. There is no nitrogen emission. But for combustion, for gasification, we can supply compressed air. So compressed air with the pressure of 5 bar. So we are maintaining pressure 5 bar by adjusting here you can maintain the pressure, here you can maintain the flow rate. That flow rate adjustment is based on the stoichiometry calculation. So from stoichiometry calculation, we can maintain the equivalence ratio. So based on that, we are circulating compressed air. So you can adjust the gap between camera. Now there will be a gap more than 5 to 6 mm. So for initiation, you have to maintain minimum gap. After arc is initiated, you can increase the gap up to 1 to 1.5 centimeters. It's 10 mm to 15 mm. The arc will be present. If it is high voltage, high current, then the gap may be 5 to 6 mm initiated. So depends on the current, the gap we can maintain. If it is more than 100, then no need of making it close. The arc may be automatically initiated. For large scale, for 100 means it affects the electrode. For larger scale unit, we can give high capacity plasma generator. So this is lab scale only. So now I can initiate the R.
Yeah. Don't see. Don't touch anything else.
How R is coming. So if I feed the waste over there, immediately fraction of seconds, only a fraction of seconds. Less than a second, it will decompose into. You could not imagine the temperature of that. Yeah, the arc near temperature, the very next layer of electrode. The temperature will be in 5K to 6K. It means 5000 Kelvin to 6000 Kelvin. Then the next layer, immediately it will freeze because the temperature is not created by as like condenser or convection. It is created based on the energy excitation of molecules. So molecule excited, so immediately it will try to back to its stable position. So its temperature is reduced very immediately. But that the spot or the zone where we generate plasma, that zone it completely discard the waste. So then next element will enter into that zone. Then it will discard. So the process will continue until complete degrades. So here you can increase the current and you can try with the different. If our waste contains more metal elements, means then you have to give a little high current for making that into slag. That slag is a slag can be recycled into further pistons or metal or blades. So everything will be converted into metal slags. Now we can look at the video how complete process how we are extracting syngas from the reactor that we will look. So this is mixture of waste. This is mixture of waste which was taken. Ten kg reactor. Once it initiated, immediately the syngas will come out. Thing is already attended one EVT program with my professor and we demonstrated the things in IT Hyderabad in front of our higher education minister. We got appreciated and It reacts with batch state. If you feed it continuously, then it will run continuously. Complete setup. The electrode arrangement. Is that
On the raw materials,
actual speed of the flame is this only. If you converted into that gas may be employed in IC engine or we may use it in boiler. But that gas is not, it won't give any harm emission as like our solid combustion. We'll go to cold one. அந்த
Switching box தேவையில்லை
அவ்வளோ இந்த போர்டில் 3 phase மட்டும் 3 phase இங்கே மட்டும் Yes, sir, yes.
Director demonstration நம்ம மட்டும் சொல்லுங்க மற்ற கதைகள் பழைய ஸ்டோரிஸ் சொல்லுவாங்க ஆல்ரெடி சொல்லியாச்சு திரும்ப சொல்லுவாங்க ஃப்ரெண்ட் ஆயிடுச்சா So we have seen how the hot thermal plasma system works, and we are going to give the demo on the cold plasma from the system and how the ammonia can be generated and in the single reactor and how it is going to be separated out, and it is going to be given. I think Sarana will give the demo of that.
So in this session, we are going to discuss about that nitrogen flow regulation. So with respect to the nitrogen flow, how that ammonia generation and the plasma will be variable. So here, when we are giving here the plasma medium is nitrogen. So we are giving the nitrogen gas so that it will become a plasma and it will dissociate. It also dissociate the water particles also, and it will be combined with the hydrogens and it will be forming the ammonia. So here I am going to start the demo by supplying the nitrogen for the ammonia generation. 2 seconds pressure and make here plasma reactor is filled with the water already and it is having a high voltage electrode and ground electrode. So between time the electricity will be passed and the gas is also moving through it. So when the electricity is passing through the gas, that becomes plasma. So that nitrogen becomes hydrogen ions. It will be excited because anything like that. And also it will dissociate the water particles into hydrogen and it will be linked to each other and it will form the formula. And the nitrogen flow will also affect the stability of the plasma, intensity of the plasma, and the duration also. Stability time, duration and the will be affected. If we give a maximum amount of nitrogen, most of the nitrogen will be released. And if we give very less amount of nitrogen, that also will influence the plasma intensity. The plasma will be very minimum and it will not efficiently produce the ammonia. So what we need to do is we should not supply more amount of hydrogen as well as very low amount of hydrogen. So we need to find the ammonia supply in such a way that ammonia production will be efficient. Here I have set to 500. So the nitrogen gas is flowing to the and the plasma is generated. So here we increase the nitrogen flow maximum so that the intensity of the plasma will be more. And if we fine tuning that nitrogen, so what will happen? Ammonia generation will be properly generated. So no more waste of nitrogen gases will be there. And the hydrogen also, when we are supplying the electricity, that will be excited into N star, that is the excited hydrogen, and N2 plus hydrogen. And it also will not only produce the plasma, the plasma is also dissociating the water into hydrogen molecules. It will be combined and will be producing the ammonia flow. So that we have explained earlier. So that is something nitrogen concentration. Activated we can control over the nitrogen. So the nitrogen is acting as the plasma medium, it's playing a vital role in the ammonia generation. So without nitrogen, that raw material for the ammonia will not be there. So here we are focusing on that regulation and improving the ionization. So when we are giving sufficient amount of nitrogen, the ionization rate also will be improved. So that the required amount of nitrogen will be available for the hydrogen, which will be the hydrogen. 5 minutes to break the city cycle. So during that time, the nitrogen will become the plasma. Afterwards, it will be okay, I guess. Oh, obviously, we also supplement using radiation for the water content. That will enhance the ammonia production. The gap between the electrolyte water, it will be rising in the water. The gap is very low, the voltage actually is very low only. Afterwards, the plasma. Starting the plasma, we need to make use of this radiation also. So here we are having three different UV variants. So here we parameter. Here you will see and we are supplying. So that gets it. We cannot give all. We can give all the variables, but we are going to optimize the variance for particular variant how much ammonia. Also, we are using new variant.
Also, we have taken this with this UV system. Once the valve is open, then we could not pick up whether you even you turn on the you could not turn on the light. So there are those safety protocol is all available. Also, anywhere if any grounding problem. If grounding problem is not, there will be chance of any accident. So if grounding is as you see, then we could not turn on the entire system. So those safety protocol is all individually arranged. You have to take it manually. So automatically, if everything is perfect, then only it will turn on. And also here we need to open while initiating the on. You can change by using current. The current value will increase, and at the initiation the current will drop slightly, and then again start increase. So that slight drop. For example, it increased up to 2.9 and it will decrease to 2.4 or 2.3. Again, it will increase to 0.6, 2.1. So the peak will come like. So based on that, we can be able to identify the now discharge is initiated.
Even it is an on, so when you open it automatically on in order to prevent the accident.
Time is over. The 5 minutes is over. After we hit the set time, it automatically. You can set time 5, 10, 30, 1 hour.